is there, right? Gomati, what is AC voltage regulator? Gomati, what is AC voltage regulator? If you don't answer, what I should consider for that? Nischal, if you can't unmute or if you don't have mic, you can type in chat box at least. Nischal, Shivraju,
Yes, ma'am.
what is AC voltage regulator?
Which can vary the AC voltage, ma'am.
Which can vary AC voltage from one level to another level. Yeah, AC voltage can vary the RMS value of the AC voltage, which will be fixed at the input side. Output side, the AC RMS voltage can be varied. So what we are going to do in this experiment is, we are going to understand how a SCR present in single phase control rectifier and AC voltage regulator can be turned on using digital triggering circuit. Okay, the first step what we are going to do is, we are going to understand how we can trigger, or we are going to develop a digital triggering circuit to generate firing pulse for the SCR, which is present in single phase rectifier circuit and AC voltage regulator circuit. So the first part, we are dealing with the control circuit. Okay, control circuit is nothing but triggering circuit. It will generate firing pulse for the SCR. This pulse we will be giving to the SCR, which is present in single phase control rectifier as well as in AC voltage regulator. Okay, let's see the aim of the experiment. The aim of the experiment is to generate firing signals for SCR using digital circuit. Okay, that's the main thing. That's the whole focus of the experiment. The whole focus of the experiment is to generate firing signals for SCR using digital circuits. What do you mean by digital circuits? Shreyas? Shreyas, what do you mean by digital circuits?
Using digital circuit gates from.
Using digital gates. Okay, using digital gates, we are going to generate firing pulses. By varying or by delaying those firing pulses, we can fire the SCRs, or we can turn on the SCRs at a required angle. Okay, by changing the angle of firing, we can change the output voltage. This is the whole idea of designing digital triggering circuit and to generate firing pulse for the SCR. The second objective of this experiment is to trigger single phase control rectifier. Okay, using the firing pulses what we generated using digital triggering circuit, we will trigger the SCR present in single phase control rectifier. After that, the same firing pulses we can apply to SCRs present in AC voltage regulator, and we are going to observe how the circuits are going to behave. We are going to note down the voltages. We are going to plot few graphs. First, let's understand how this digital triggering circuit is going to work. Okay, one thing what you need to remember here is, if you observe the figure, what it is displayed on the screen, you can observe two voltages, right? What are the two voltages that you can observe on the screen? Are you able to see two voltages on the screen? Observe the screen. You have two voltages mentioned there. What are the two voltages?
15 volts AC and
15
DC.
volt
Yes, ma'am.
AC and DC.
15 volts.
Yeah, 15 volts AC and 15 volts DC. What is the single phase supply available for us? What is single phase supply available for us?
230 volts, 50 hertz.
230.
230 volts 50 hertz is the single phase supply available for us. So that 230 volt single phase 50 hertz single phase supply is stepped down to 15 volts AC first. Okay, in this kit you will be having transformer built inside. That transformer will convert 230 volts AC to 15 volts AC, and it is provided here. And we'll be having one rectifier also, inbuilt rectifier, which it is not shown in the triggering circuit because it is not a part of triggering circuit. This transformer and rectifier are not part of triggering circuits, so it's not shown in the uh, display picture. Okay, whereas rectifier and transformer will be present in the kit, in the module. You have not seen any module till now, I guess, right? Kit in the sense where you might have seen is 1 second. Let me check. If I could get, it's fine. Or else we will continue with the explanation. Okay, we'll be having kit something, this one. The same thing we have in our laboratory. Okay, like this we will be having kit. Let me open it. I hope you can see, right? You are able to see the screen, right? Yeah, kit will be something like this. It's like a box. Okay, down we have, they have shown only the face of the kit. Down you have all the components that are displayed on the upside. Or one more, I can show you if it's possible. Yeah, it will be something like this. Yeah. See, on top, you are able to see the circuit diagram and the places where you can connect. Below, you have something like box kind of thing, right? Okay, inside this box, we'll be having all the components, what it is displayed over the screen here. Okay, this is the display screen. All the components will be inside. Connecting terminals will be provided on the top. Okay, now the display picture, what I have shown here in the PPT, does not consist of transformer and rectifier, but it will be inside the kit. Okay, why they have not displayed transformer and rectifier here? Because they are not part of control circuit, so they have not displayed. That's it. Okay, the 230 volts plug will be available like this. There will be one socket here like this. Okay, one 230 volt socket. You have seen the plugging wire, right? You can see here. Okay, like this one socket will be provided. Two terminal socket will be provided along with this kit. We can plug it to 230 volt supply, and that 230 volt supply will be stepped down to 15 volts AC. That transformer will be inside the kit, and along with that one rectifier will be there which converts AC to DC. 15 volts DC will be provided. Okay, these two things will be inside the kit. And one thing what I wanted you to ask is why we need to reduce 230 volts voltage to 15 volts AC? Why we need to reduce 230 volts voltage to 15 volts AC?
The kit's maximum
Digital
value.
sensor work DC.
DC supply is fine. I'm not asking about DC supply. I'm asking about AC supply. If you provide directly 230 volts,
The
whether
kit
this
will
can
the kit will get
get damaged?
damaged. So that's why for 15 volts they'll be using it. I think.
I can design the other components also for 230 volts rating.
To reduce the harmonics, ma'am.
To reduce harmonics, you have to deal with frequency. Not
Triggering is nothing but with a small voltage. So
yeah. For triggering, we need only small voltages. We don't need high voltages. Okay, there are two parts in your there are two parts in power electronics. First thing is power circuit. Second thing is control circuit. Power circuit always deals with high power levels. Control circuit deals with low power levels. Okay, if you give 230 volts here, the output signal what we get also will be of very high voltage magnitude. If you give that much high voltage magnitude to control terminal gate, the losses that develops at the gate, it will be more, and that much energy is not sufficient for the valence electrons to cross the depletion layer. Lower levels is sufficient for the valence electrons to cross the depletion layer. If you give more voltages, then the dissipation in the device will be more and the device will get damaged. So always we will take consider any control circuit, the voltage levels will be very low. Okay, this is a very important viva question, why control circuits will be designed for lower power levels and why not higher power levels, because we need only less amount of energy to excite the electrons to jump the depletion layer. Why we are giving gate signal? Why we are giving gate signal? What will happen in BJT if you give base pulse? What will happen in BJT if we give base pulse? Okay, let's consider this is the base BJT. You have provided the supply, right? Okay, if you provide gate pulse, what will happen inside the BJT? Initially, when you are not providing this voltage, when this supply is absent, junction J1 and J3 will be forward biased. J2 will be reverse biased, so there won't be any current flow through the device. Once you give this power supply, once you give the gate supply, then current flow through this will excite the electrons present in junction J2 and they'll cross junction J2 and they'll move to junction J3. Thereby the current starts to flow through BJT. Okay, for that excitation of electrons, we need only little energy. We don't want more energy. So we always go with lower power levels when it comes to control signal. Okay, this is the only point what I want you to remember. If you want, you can note it down somewhere. Always power circuits will be at higher levels. Control circuits will be designed at lower power levels. Now, why we need this DC supply? Why we need this DC supply on the kit? Why we need this DC supply on the kit? Hmm? Why we need DC supply here? First thing what we identified is we have two supplies provided at the on the kit. One is AC supply, another one is DC supply. Now we understood why we have reduced the voltage level of AC supply, and we will see how we are going to make use of this AC supply. Now my next question is why we need DC supply on this kit? Because the control circuit what we have is a digital control circuit. We are using many digital devices. Okay, ZCD, oscillator, all not oscillator, counter, then flip-flop, all these things are digital devices. Okay, in order to work any digital device, we have op amps also inside the IC. If we want to make these ICs operate, We need DC supply. For that we have DC supply. Now we'll try to understand control signals will be generated using this digital triggering circuit. When you plug in 230 volts socket into the main terminals, the power starts to flow through this path and to this path. This will energize the ICs. Now this 15 volts AC will be will be appearing across these two terminals. Okay, now if you observe, this is connected to this terminal and one second. Okay, now this is connected to this terminal and this terminal. What is this? ZCD. What is ZCD?
Zero cross detector.
Zero crossing detector. As the name indicates, what it does. You have studied it in LIC, right? Now, what is the waveform available at this point? It will be a sinusoidal signal. What is this 15 volts? Is it peak value or RMS value? Is that 15 volts peak value or RMS value? Varsha?
Ma'am, peak value.
Peak value. It's not peak value, it is RMS value. Okay, make a note. It's RMS value. Wherever the AC supply ratings are provided, all those values are RMS values. So this 15 volts AC is RMS value. If the RMS value is 15, what will be the peak value? Anyone calculate and tell first? What will be the peak value, peak of the sine wave? If the RMS value at the supply side is 15 volts, what will be the peak value? Calculate and tell. What is relation between RMS value and peak value in a sinusoidal signal? What is relation between RMS value and peak value in a sinusoidal signal? VRMS
RMS equal to 1 by root 2 into peak value.
Vm by root 2. Vm by root 2.
No, VRMS is equals to peak value by root 2.
What Vm is peak value. So how you are going to calculate it? Vm equal to Vm is peak value. Vm equal to root 2 into VRMS. Calculate it and tell this value. 15 is VRMS. Into root 2 you do what you will get?
325.
10.6.
Huh? VRMS is 15. It's not 230. From 230 we have stepped it down to 15. Rishikesh.
21.21.
21.21. VRMS is 15. 15 into root 2 is 21.21. So at this point, a sinusoidal signal with a peak value of 21.21 will be available. Now, when you apply this signal to zero crossing detector, what will be the output?
Only positive waveform.
Positive
Square
full
wave.
pulse will come. Square wave like this, you will get. It will detect at this point, it is crossing 0. It is crossing 0, so 0 crossing detector, it will detect. Or it may give pulse like this. Okay, now at this point also it is crossing 0, right? Then again it should detect. So you'll get a pulse like this. Okay, the 0 crossing detector output will be getting pulses like this. Okay, whenever it crosses 0 towards positive side, 0 crossing detector will detect and it will produce a pulse like this. Once again, when it crosses 0, when it is going towards negative cycle, 0 crossing detector will detect and it will produce a pulse. Now, when now this pulse is going to reset button of oscillator. Okay, now let's move to other part here. The same supply, it's given to sine to square wave converter. Okay, we have sinusoidal signal here. It's given to sine to square wave converter. So it has two outputs. Sine wave A indicates during your positive half cycle, this part is converted to square and it will appear here. A dash is its complement, it will be appearing like this. Okay, during negative half cycle, it will get converted into square wave and its complement will be appearing here. Okay, now for oscillator, the reset signal will be coming from this side. As soon as the supply crosses 0, the oscillator will get reset. Now, here what we have the digital input. You have seen digital kit, right? In your electronics lab, you have seen digital kit. You have switches. You had switches like this. When you turn on, it will become red, green. It was becoming red. Like that, you will be having 4 switches here. Okay, using which you can set any binary number or any number between 00000 to 1111. 0000 indicates you are 0 degrees. 1111 indicates 180 degree. Okay, initially let's say the binary number is set to 1 0 0 0. You can set it to any value and you can switch on the circuit. You can set it to 0 0 0 0 1 1 1 1 or 1 0 0 0. Any value you can set and you can turn on the supply. Okay, before switching on the supply, you can set it to any value. Once you switch on the supply, this is the scenario what it's going to happen. The AC supply will appear at the terminals of ZCD. ZCD will provide signals like this, and the same supply will be appearing across sine to square wave converter, and at the output of sine to square wave converter, you will be having signals like this. What sine to square wave converter is doing? It will detect positive half cycle and it will produce a pulse here, and it will detect negative half cycle and it will produce a square complement of it at A dash. Now, here we have a binary counter. It is a 16-bit counter. That's the reason why we have 00000 to 1111. Okay, if you count, you'll be having 16 numbers in between 0001001 00011. Like that, you'll be having 16 till 16 count. You will get it from 00000 to 1111. You'll be having 16 numbers. So we are using 16-bit counter here. As you change each number, it will produce that much delay. It will produce 16 pulses actually. Okay, the output of this binary counter is 16 pulses. Like this, it will produce 16 pulses within 180 degree. Within 180 degree, it will produce 16 pulses. If we set this binary value to 0000, the pulses will start producing from 0 degree itself. If you delay it like 1000, the pulses will be produced with a delay like this. Okay, I can show the waveforms here. See. This is the sinusoidal signal what we are giving at the input of ZCD, and this is the output at zero crossing detector, not zero crossing detector, sine to square wave converter. Okay, at A and A bar, like this you will get waveforms. When it comes to output of counter, you will be getting 16 pulses in 180 in 180 degree duration. It will be producing 16 pulses. Okay, if you give the delay as 0000, if you give the delay as 0000, the pulses will start from this point because 0000 indicates 0 degree. Okay, if you give the value as 1000, What is the corresponding degree for this? What's the corresponding degree for this? You can calculate. You can calculate using this 0.001. You have here, right? Alpha equal to n divided by 2 power 4 into 180 degree, where n is its decimal equivalent. Now tell me what will be the value for 1000? What is decimal equivalent for 1000?
8.
8.
8. So n is equal to 8.
8.
Calculate what will be alpha.
90.
90 degrees. Okay. That means when you set the digital input as 1000, the delay what we have inserted is 90 degree. So the pulses will start producing from this moment. Till this moment, there won't be any pulses. From this moment, the pulses will start producing like this. Okay, like that, depending upon your value. For example, if you give this value, what is the corresponding degree? What is the corresponding degree value? What is the corresponding angle?
45.
45 degrees. Okay, that means the pulses will start from this moment. Okay, like this, the working of oscillator will be there. Working of binary counter will be there. Depending upon here, whatever the value you are giving, you are setting, it will act as delay for the binary counter. Those many degrees, the pulses will be delayed. And these pulses are appearing at first terminal of oscillator. And we have one more reset terminal here. Okay, this reset terminal is coming from ZCD, and along with that, it is going to load also. At load, what we are getting? We can see here. Okay, the output of ZCD and load is same. Okay, if you observe here, the output of ZCD is going to load and it is going to reset terminal. Okay, what is the waveform across the road? As I told, this is the output of zero crossing generator. Whenever sinusoidal signal crosses zero, it will detect and it will produce pulse. And whenever it crosses zero again it is producing the pulse. Okay, this kind of pulse will appear at this point. Whenever that pulse appears, 16 pulses will start producing. If there is a delay, it will hold for those many degrees. I hope it's clear. As soon as positive supply appears at this terminal, this ZCD will produce the output like this. Once the signal goes to this, the binary counter will be ready with 16 pulses. If there is any delay here, it will hold the pulses for those many degrees, then it will produce the pulses. If there is no delay, then the pulses will be passed as it is. Okay, like this, as soon as it reaches a signal from ZCD, load terminal, it will be ready with its 16 pulses. If there is any delay, if there is no delay, like 0000, if we give, the pulses will be passed to oscillator immediately as soon as they are generated. If you give any delay, 1000, 90 degrees, for 90 degree duration, these pulses will be holded, then they will be passed to the counter. Okay, now what this reset button is doing here is, what oscillator is doing, whenever the reset button appears, the counter won't get any, okay, the counter output will be given to this side. Okay, reset button is, whenever reset button is provided, the oscillator will provide signals to this counter. Okay, then the counter, based on the delay, it will pass the signals. Is that clear? No? Shall I repeat? Okay, ZCD will produce a signal like this. As soon as the signal is passed to oscillator, oscillator produce the signals and it will be passed to counter. The binary counter is now ready with 16 pulses, because at the same time the load command is also went to counter, so it will be ready with 16 pulses. If there is any delay, The counter will hold the pulses for that much duration, and then it will pass the signals. If there is no delay, the pulses will be passed immediately to S. Okay, let's say there is a 90-degree delay. Okay, let's say there is a 90-degree delay, and I am checking the pulses or signals at 0 degree. I hope I am clear. I have given the binary count as 1000, indicating 90-degree delay, and I am checking how SR flip-flop is going to operate at 0 degree interval or 0 degree time. Now at 0 degree, what will be the value of at S? I have given a delay as 90 degree, and I am checking the value at S at 0 degree. What will be the value at S at 0 degree? 0. It will be 0. Only at 90 degree this pulse will be passed to, only at 90 degree the pulse will be passed to S. So till 90 degree the value of S will be 0. What will be the value at R? Okay, this signal is passed as it is to R. At 0 degree duration, what will be the value at R? What will be the value of value at R? At 0 degree, it is high, right here. So it will be 1. When the input is 0, 1 for a SR flip-flop, what will be the output? For a SR flip-flop, when input is 0 and 1, what will be the output?
Reset value, ma'am. 0 and 1. Q will be 0.
Q will be 0. Q bar will be 1.
1.
So there won't be any firing pulse at this point. Q is the firing pulse which we are giving to G1, G2. Q dash is the firing pulse we are giving to this terminals. G1, K1, sorry, G1, K1, G2, K2. One second. Okay, Q we are giving to Q, we are giving to G1, K1. Q dash we are giving to G2, K2. So at G1, K1, G1 is nothing but gate 1 of first thyristor. K1 is cathode of first thyristor. Okay, you are not supposed to interchange these while doing the connections. You have to connect as it is. Okay, what is our first experiment? After generating, now firing pulses are generated. See, at Q you have 0, at Q dash you have 1. Now these signals we are giving to high control logic here. What this control logic will do is, it will check whether the signal to be synchronized to A or the signal to be synchronized to A dash. Okay, now Q dash is synchronized to A dash because A dash is high and A is having this kind of pulse. A dash is having this kind of pulse with a 180-degree delay. Now, these two pulses Q and Q bar will be multiplied to A and A bar, and they are given to G1 K1 of AC voltage regulator, G2 K2 of AC voltage regulator, G1 K1 of rectifier, G2 K2 of rectifier. Okay, here we have 4 control signals. 2 are for rectifier, 2 are for AC voltage controller. Now I am concentrating on rectifier here because we are not using these 2 terminals in lab. What's the process that goes on is, A will get multiplied with Q. Now what is the value of Q? What is the value of Q?
0.
0, ma'am.
0. So when 0 gets multiplied with AC signal like this, when it gets multiplied with 0, the voltage or the pulse at G1 K1 will be 0. So you won't be getting any firing pulse at G1 K1. Same thing you can observe at 90 degree. When 90-degree appears, at that point what will happen? 1 and 1 will appear at this point. When for a flip-flop, SR flip-flop, if 1 1 appears at the input, what will be the output?
Not defined.
Not defined.
Toggle.
Toggle. It will toggle and it will interchange the values. Like it will become 1, it will go to 0. So at this moment, Q will become high and it gets multiplied with this, and G1, K1 we will be the pulse will be appearing. So at that moment, if the thyristor will come to on state. Okay, this is how we can generate firing pulses, and we can turn on SCR using digital triggering circuit. Now, what is this control logic? What it does here is it gets multiplied the Q and A, and it will convert it into high frequency pulses. Okay, till now it was continuous signal, right? Like this. Okay, this control logic will convert from continuous signal to high frequency pulses. Convert from continuous signal to high frequency pulses, because the ideal characteristics of device is always we need pulse triggering, we don't need continuous triggering. When you go for pulse triggering, the losses in the device can be reduced. So this control logic will convert continuous signal into continuous pulses. This will be applied. Okay, this is how we can generate the firing pulses. Now let's see how to do the connections. What is the circuit here? It is AC voltage, single phase, half controlled rectifier, right? We have 230 volts power supply.
Excuse me, ma'am.
Yeah.
Ma'am, in SR, 1 state should not be allowed, no, ma'am. JK toggles.
Yeah, it toggles. So whenever 1 state appears here, that is flip flop. That's not flip flop. That's latch. In SR latch, it will toggle.
Yeah.
In SR flip flop, the output will be changed from 0 to 1.
That is JK, no, ma'am. JK flip flop, it will change from 0 to 1 and 1 to 0. Toggle state.
No, I guess in SR latch it will happen like toggling, not toggling. No output. Output won't be defined in SR latch. In SR flip flop, as far as I know, it will change from 0 to 1. Check out once, even I'll check out and we'll see. Okay, till now, because as far as I know, in SR latch, it will happen like that. In SR flip flop, when 1 and 1 appears, the output will shift from 0 to 1. Okay, that's how the operation is going on here. Check out once. We will discuss about this in next class also, if required, this SR flip flop. Okay, right now let me finish the connections. Okay, let's assume this is AC supply from the main terminals. Okay, this is the main terminal AC supply we will be having, and you will be provided with 2-plug pin. You will be having a pin like that, and it will be having 2 terminals. Okay, supply terminals you will be having. You will be provided a plug point. You will be placing it to holder, and you will be getting 2 terminals here. One terminal you will be connecting to anode of T1, and K1 you will be connecting it to load, and the load other terminal you will be connecting back to supply. I'm showing the connections here because this is the same, this is the circuit diagram which you see on the kit, and you'll be doing the connections like this only using the wires. You use the wires in analog electronics lab, right? The same wires, using the same wires, you'll be doing the connections. Okay, you'll be having plug, we'll be giving the plug, you will be connecting it to 230 volts main supply. The plug will be open with 2 terminals. One you'll be connecting here to anode of thyristor, and from cathode you will be giving it to resistance. From resistance it will be going back to supply, and from G1 you will be connecting it to G1, From K1, you'll be connecting it to K1. Then when you switch on the power supply and when you change the values, initially you can keep the switches in 0000 position. Then you will observe the waveforms like completely sinusoidal. Since it is half controlled rectifier, sinusoidal supply is the supply. You'll be getting a waveform like this. When you change the binary count to 1000, you will get a waveform like this, 90 degree. When it is 0100, you will get a waveform like this. Okay, this is how you can make the connections. Connections are very simple, but the only care what you need to take is while giving this 230 volt supply, while giving this GK. Okay, it should go to GK. If you give it to G2, K2, it won't synchronize. Whenever the thyristor is in on state, it won't receive firing pulse because G2, K2, the firing pulses at G2, K2 will be delayed by 180 degree duration. Okay, so when you connect it to G2, K2, thyristor won't come to on state. So always you should give it to G1, K1. And one more thing is this 15 volt supply, you have to be very, very careful. Wherever you have 15 volt supply, you have to make sure that either inbuilt transformer is present or you have a separate transformer, external transformer to convert 230 volts to 15 volts. Okay, this is how you can make the connections. Okay, this is the actual circuit. We have 230 volts supply, 230 one terminal is connected to cathode is connected to load. Load is connected back to other terminal of supply. G1, K1 will be going to the control circuit as I shown in the circuit. Okay, then by varying the value binary count from 000 to 1111, you can calculate alpha. Yeah, Rishikesh. Harshal.
Yes, ma'am, I've checked it, ma'am. Here they have given that when both inputs are 1, output will be in invalid state. It goes to metastable state where they couldn't predict output, ma'am.
They
In
can't
JK
predict.
output in JK flip flop, it will toggle, ma'am, 0101 like that.
Okay, but in the kit what we are using, it is SR flip flop only. They can't determine the state, but here what's happening here is the state will change from 0 to 1. They have mentioned they can't determine the state, right? But in this case, this is how the operation is going on. As soon as the pulse appears at this point, the output of this is going to 1. This is coming to 0. We can see practically in lab when 1 appears, Q goes to 1. Okay, you have one more this also waveform. 1 second, let me show that. Okay, whenever alpha and then the pulses appears, Q goes to 1. The same signals you can observe in the kit. Okay, they have shown it's not possible to determine theoretically, but practically when you check, it is moving from 0 to 1. Is this fine?
Yes, ma'am.
Okay, theoretically we can't predict what state will come, but practically it is coming as it's moving from 0 to 1. Okay, now this is how your signal will be taking down the readings. N is nothing but the binary equivalent. N is nothing but the binary equivalent. We'll calculate alpha. VDC will be calculating using this theoretical formula. Practically, we will be measuring using the multimeter. Okay, multimeter will be connecting across the load resistance. We'll be noting down the values practically. Theoretically, we will be calculating using this formula. Okay, we'll be calculating alpha for each binary count using this formula and we'll be substituting this here. Vmax you can note down. 230 volts is the RMS value. You can measure it from the CRO. Okay, you'll be observing the waveform in the CRO. You can note down VM. Blindly don't take it as 230 into root 2 because 230 is the ideal value. Each and every time we won't be getting 230 volts RMS at the supply. It could be sometimes it could be 220, sometimes it could be 225. So always before calculating the readings, you note down what is VM. Right. Next we have AC voltage controller. We have seen in the control circuit, we have seen G1 K1, G2 K2, right? Two signals are produced. The same thing we are using for AC voltage controller. Okay, I can show the circuit in kit itself. Here itself I can show the circuit, how to do the connections. I can't erase it now. Okay, I don't think I can erase this. It's fine. 1 second. Let me take it out, and because these connections are important, otherwise there's no meaning in explaining this here. I can show the connections now. Okay, we'll be having AC supply, and from AC mains you will be doing the plug connection. With plug you will be having two ends. What we do, how we do the connections in AC voltage regulator is one terminal will be connecting to A1 and A1 will be connected to K2. Back-to-back connection will be having. You can observe here, we have back-to-back connection. Okay, anode of one thyristor is connected to cathode of other thyristor. And then cathode of one thyristor, anode is connected. From this connection, it will be going to resistance. From resistance, it will come back to main supply. Okay, from G1 to G1, even for AC voltage regulator in lab, we are using firing pulses generated for rectifier only. Because this is not in working condition, we can make use of this. G2 to G2, K2 to K2. Okay, like this you need to do the connection. These connections are very important. If there is any mistake in the connections, it will damage the thyristor. We need to replace the thyristor or the circuit won't come into working condition. Okay, this is how we do the connection. Now by varying this 100000000, the firing pulse can be varied for both T1 and T2 thyristors, and we can note down the readings in the tabular column. Okay, we can note down the readings, calculate alpha, then you can measure V naught RMS. Here we are not going with any theoretical calculation because the formula is too complex. AC voltage regulator RMS value formula is too complex, so we are not going with theoretical calculation. We will measure practically using multimeter, keeping it in AC mode. Okay, this is all about the experiment. After taking down the readings, you have few graphs. You need to plot alpha versus VRMS. And in previous case also, you need to plot alpha versus VDC. Practical values. Okay, whenever you are drawing graphs, it is using practical values. Okay, and then we will observe as alpha varies how output DC voltage and how output RMS voltage are going to vary. Okay, this is all about this experiment. Let's discuss about the next experiment in next class. I hope it's clear, right? This is the lengthiest experiment what we have in first cycle. Okay, if you have any doubts, you can ask, or else we will close the session and we will continue in next class. Let me take down the participants. Okay, students, then we will continue in next class. Thank you.
In this video, we will be learning the conduction of digital triggering scheme connected to the rectifier circuit as well as AC voltage controller. Now we have the transformer here. It's a 15 0 15 transformer. We have taken the points from 15 and 0. So 15 volt AC is fed to the as an AC input to this particular module. You can see here 15 volt. 0 to 15 volts we can give it here. As well as we are going to provide the DC voltage of 15 volt, nearly 15 volt. We are giving the DC voltage to this particular module. So we are providing both AC and DC. So 15 volt AC will be provided here and 15 volt DC is provided here. And this is the module for your digital triggering scheme which will generate the triggering pulses. Now let us see the waveform one by one. Let me connect these CRO points to the AC points. I am measuring the AC voltage and you can see the AC voltage waveform. So let us measure the amplitude of this waveform. The amplitude is 2 units from the zero reference. Let me show the ground point. Ground point, and let us see the amplitude is 1, 2. 2 units are there. 2 units into, we have kept it in the 10. We have kept it in the 10. So 2 into 10 is 20 volt. 20 volt is a peak value of this sine wave. But we have given 15 volt AC here. The 15 volt stands for the RMS voltage. So 15 volt from the transformer into root 2 when you perform, you are going to get the 21 volt theoretically. Practically you are getting 20 volts. But there is no guarantee that we are getting 15 volt AC. So we are getting practically 20 volts AC peak value. RMS is 15 volt for this. Let us measure the time period for one cycle. For one cycle, you can see that how many units here is there. 1, 2, 3, 4. 4 units are there. 4 units into the time division is here is a 5 millisecond. 5 millisecond. So 4 unit into 5 is 20 millisecond. 20 millisecond inversion is nothing but 50 hertz. Right? So we could able to see the sine wave whose amplitude is 20 volt and frequency is 50 hertz. Now let us see the waveforms of the DC side. Now I connected the DC voltage waveform. It's showing, let me ground it, 0, it's jumping to around 13. So 13 into your 10. So it's showing 13 volts, 13 volt DC, 13 volt DC voltage. Now let us see the waveform across your square wave. Now we are converting this 15 volt AC to the square wave. A and A bar are the complement of each other. Now let me connect your positive probe of the CRO to the A. The negative probe must be connected to negative terminal of the VRPS. Don't connect it to the AC point. That is wrong. Your negative probe has to be connected to the 0 point of the 0 point. You can see of the DC supply. So the same wire, red color wire is going to the VRPS here. Red color here stands for the negative voltage. Now let us see the A waveform, square wave. Square wave we are getting around 0.7. 0.7 into 10. So we are getting 7 volts here, square wave. Now I convert it to the A bar. So A bar is a complement of that. So A bar I convert the CRO probe to the A bar. So I am getting here 1 unit. 1 unit into 10 is 10 volts. I am getting 10 volt. Then countdown pulses. Countdown pulses is the output from the oscillator. You can see oscillator is kept on generating pulses at the rate of 16 pulses per half cycle. You can see the train of pulses. So you can see there is a glitches there at some points. So between them there will be 16 pulses. These are used as the clock pulses which are fed to the countdown counter. So you can see the countdown pulses are given to the counter here. Counter. Then next we measure your load bar or reset. Load bar reset point. Let us see what kind of waveform we get here. You can see load bar reset is 0 at 0 degree. Again from 0 to 180 it will be high. again goes to 0 at 180 degree, again at 360 it becomes 0. This is an indication that at every 0 crossing there is a load bar which is going to 0. You can see. So it is occupying 2 units. 2 units at 0 degree, 180, 360 is going to 0. Load bar. At this particular point, my whatever the preset data we are going to load it here. So this is 1, 3, 5, 7. This preset data at 0 degree or 180 degree, it will be loaded into the counter. And the countdown starts because the clock pulse from the oscillator is already fed there. Okay. Now let us see the waveform across the borrow. How the borrow works is that once the countdown, whatever the binary preset data we have fed to the counter, when it goes to 0, then one borrow will be generated. This borrow is fed as an input to the SR flip-flop. It's going to set the flip-flop and output will be high. Output of the Q will be high when the borrow is generated, when the countdown goes to 0. So let me show you borrow pulses. This is a borrow pulses which is constant. Borrow pulses will be generated when the countdown goes to 0 value. This borrow pulse is fed as an input to the SR flip-flop. So let us see the output of the SR flip-flop. SR flip-flop output you can see there. I'm changing the data now, kept on increasing the data. Now time being my digital data is 0, 0, 0, 0. All of them are 0. Then my firing angle is 0 degree. We can see at 0 degree only the pulse is started. On time is more now. Now I kept on changing. You see in the CRO. So this is 1, 3, 7, then 15. At 15, on time is very less compared to off time. Again go back. This is 7. On time is increasing, further increasing, it's become maximum. Now the Q output is 1 into 10. So we are getting 10 volts. Q bar output is complement of that. So Q output you observe, on time is more than off time. Q bar is the reverse. On time is lesser than the off time. My unit is 10. So 10 into whatever the value you have is 1 unit. 1 into 10 is 10. So both are 10 only, Q bar. Let me show you the pulses at the G1 K1 of the rectifier. So what is G1 K1? These are isolated pulses. At the control logic, you have a chopping circuit as well as the isolation circuit. Isolation circuit is going to isolate your power circuit with the control circuit. This is our control circuit. This control circuit has to be isolated from the power circuit because control circuit is very costly than the power circuit. So many electronic gadgets are there. G1 K1 is the firing pulses. You can see the firing pulses. I am showing very near. And then let me change the values. Suppose I am going to 1, 3, 7. Then you can see the on time of the firing pulses is reducing there. And this is 15. At 15, you are getting a small spike there. So respective firing angle is increased towards 180 degrees. This is G1 K1. Let me show the values for a 8. G1 K1. Go for G2 K2. G2 K2 also we are getting firing pulses. So these firing pulses, G1 K1, G2 K2, we can give the firing pulses to your full bridge rectifiers. So consider the power circuit shown here. The phase is fed to the anode of the SCR. Cathode is connected to the load. Load we are using is a bulb. And then another point of the bulb is fed back to the neutral. So we do the same connections. The 230 volts wire is connected to the anode. This wire is the phase of the AC supply. Anode. Then cathode. The cathode wire from here goes to the bulb point. The bulb point here. Then the return path is this is the neutral wire of the 230 volt supply. So this is 230 volt supply which is taken here. 230 volt wire which is coming from the source. There's a Bescom point taken from here. Now in this circuit the SCR conducts only during positive off cycle. Negative off cycle it won't conduct. So we can expect only 50% of the DC voltage at the output. Now we know that the digital circuit, the binary data is proportional to the firing angle. You can see the binary data is 0, 0, 0, 0. Then alpha is 0. Alpha is 0. Let me show you the output voltage waveform here. ಇಲ್ಲ ಇದು AC ಆಯ್ತಲ್ವಾ I am talking load point. You can see here in the CRO we should put it in the DC mode. If it in AC mode it will show the AC content. This is a DC mode. You can see the complete half-wave rectifier output where firing angle alpha is 0. And let me change the digital data here, binary data. Let me change it to 2. 0010 means 2. So you can see there is a chopping of the waveform that's happening at 36 degrees. 36 degrees is the firing angle. You can see here. So I'm keep on changing the digital data. You can see expect the cutoff of the waveform. This is a 6 for digital data 6, and I'll go for 8 now. For 8 we can expect alpha 90 degrees. Alpha 90 degrees. Then I am further increasing the digital data to 12, 14, and then when you go for a 15, very minimum RMS or a DC voltage is expected the output here. Now to measure the firing angle, let me take one of the case where I kept the digital data is 1000, nothing but we can expect 90 degree alpha. So physically we can measure alpha is 90 degree, or otherwise we set the time zone to 5 milliseconds. The node 5 millisecond whenever you put it, which means that every time division is 90 degrees. This is 90 degrees. So 5 millisecond means 90 degree, 20 millisecond means 360 degree, because supply frequency is 50 hertz, inversion of that is 20 milli. So 20 milli corresponds to 360 degree. So we have put the time division to 5 milli. 5 milli means every unit is precisely 90 degrees. If at all you put it at 20 millisecond here, 20 millisecond in the knob, then here every unit corresponds to 360 degrees. So let us keep it in the 5 millisecond, and we can see the firing angle properly. You can see at 1 unit, after 1 unit we can see there is a rise in the waveform. 1 unit corresponds to 5 milli, 5 milli means 90 degree we are getting. So physically we can inspect, or else by using the formula, the firing angle alpha n is equal to n by 2 to the power of n into 180. From that also we can get it. So we have this formula. Using this formula also we can calculate theoretically. We can substitute the values firing angle and respect to DC voltage. We can note down here. So firing angle theoretically we can put it, as well as practical also we can verify here. So this is the experiment with respect to the off control rectifier is concerned. Now the next part, in the same experiment we are going to do the AC voltage controller. AC voltage controller. So this is a circuit of AC voltage controller, so which is going to vary RMS value of the output voltage. Input is AC, output also AC in nature. So in case of AC voltage controller, two pharisors are conducting anti-parallel. So the T1 conducts during positive off cycle, T2 conducts during negative off cycle. First let us note on what's the peak value and the frequency of the supply voltage. Let me go to the CRO. So this is the supply voltage. In fact, this connected to the output point. When my firing angle alpha is 0, my output and input both will be same. Now let us count the number of units covered for your measurement of the peak. 1, 2, 3, 3.2. So 3.2 into 1 here. 3.2 into 1 is 3.2 volt only. From the alternator we have kept it 100. So 3.2 into 1 into 100 is 320 volts. 320 volt is the peak value of this waveform. So this alternator, this is a power scope wherein it's going to downsize the voltage to 100 times or 10 times. We have kept it 100 times, so that 320 volt will be available as a 3.2 volt in the CRO, because 320 by 100 is 3.2. We can see only 3.2 volt over here. Frequency measurement. For frequency measurement, keep this from the 0 reference and see how many units you take along x-axis. So let me keep it at the 0 reference. So it is 1, 2, 3, 4. 4 units into 5 millisecond. So 4 into 5 millisecond is 20 millisecond. So for all the AC voltage measurement power electronic converters, you keep the time division at the 5 millisecond. When you keep it at 5 millisecond, every unit corresponds to 90 degree. In one unit there are 5 subdivisions are there. Every subunit corresponds to 90 by 5, that is 18 degrees. 18 degrees. Now let us see some examples. Now let me set the binary data as a 0010, 0010. Then so when you keep it 0000, input is equal to output. So CRO is showing 220 volt AC RMS voltage. Now I keep it for the 0010. The voltage is reduced to 213 volts. 213 volts. You can see there is a chopped voltage waveform, and this chopped voltage waveform somewhere at after 2 subdivisions it has raised. It has raised after 2 subdivision. Up to 2 subdivision it is 0. After 2 subdivision it has increased to the higher value. So this respective, from here we can measure the firing angle alpha. So 18 to is 36 degrees. As I told you, 1 unit is 90 degree, 1 subdivision is 90 by 5. It is nothing but 18 degrees. 18 to is 36 degrees. Roughly 36 degrees is the firing angle alpha now. Now I said this is 6. Let us say this is 6. 0110 is 6. The voltage is gone down to 153 volts. In the illumination of the bulb is reduced here. And you see there is a more firing angle. Firing angle is increased here. It's almost 18 forza. 18 forza. 18 forza is how much? 72. 72 degrees. 72 degrees. Let me set for 8. 8 is 1000. What is further reduced to 110 volts? Then you can see here one complete unit. You don't have a waveform. It's 0. So that is a 90 degrees exactly. 18 phi is a 90 degree. It's a firing angle alpha. Then let me go to the value 12. One of the reading is 12. 110 is 12. 12 means the voltage has gone down to 29.7 RMS value AC voltage. The illumination of the bulb is very less now. It's very less. Let me see the firing angle alpha. So 1 unit, 1.2, 1.4, 1.6. So 1.6 into 5 milli. Is whatever the 1.6 subunits are there into 5 milli. So 1.6 into 5 milli, you are going to get the respective. That is 1.6 is nothing but 1.6 is 18 degrees because every subunit is 18 degree. 1.6 into 18 degree, you are going to get around 144. Check it up. The 1.6. Sorry, that is a 5, 6, 7, 8. 8 into 18 degree. Madi. 5, 6, 7, 8 into 18. 144. 8 into 18 is, as I told you, every subdivision is 18 degree, right? So 5, 6, 7, 8. 8 into 18 is 144 degrees. So 144 degree. So the voltage is very, very less, 29.9. And the illumination is very, very less. Let me go for the one of the last value, 14. 1110, 1110, 14. The voltage is very less, 7 volt. You can see the illumination is very feeble. So red hot, tungsten has become red hot. It's very feeble. And even firing angle you can see somewhere around. It's around 9 subunits. There is no voltage. 9 to 10 subunit became a small voltage. So 9 into 18 is 162. 162 degrees the firing angle now. So in this way we can conduct this experiment. So here what we have done, we have connected both the SARs in anti-parallel. 2 SCs are available in the same block. We have connected the anti-parallel and we have rigged up the circuit.